All right, number 8. So I was looking at this problem a moment ago, and I realized that it's a little bit there. It probably should have been written differently, but we'll get into that. We can still do it though. Um, so the issue is that some of this, the statement of the problem is a bit confusing. Anyway, as it says, the number of mosquitoes in an area of southern Georgia can be modeled as a piecewise linear function of rainfall in centimeters. An initial sample is taken when rainfall is measured at 0 centimeters, and there are estimated to be approximately 0.4 million eggs per acre. After 9 days of heavy rainfall, the number of eggs is estimated to be 0.89 million eggs per acre. The number of eggs per acre varies linearly with rainfall. The rainfall peaks after 2 weeks. After 2 weeks, the number of mosquitoes per acre begins to decrease at the constant rate of 0.07 million eggs per day. So when I see piecewise linear function and I don't have a graph, I think, well, I'm going to need to make a graph. So here's where the problem comes in with this question. When I try to make the graph, the first thing you have to decide is what are your axes going to be? What are they going to represent? So the vertical axis is clear. It's the number of mosquitoes in millions per acre. This is eggs, right? Millions per acre. But then the horizontal axis is a bit more mysterious because the question says it's a piecewise linear function of rainfall. So, we could put rainfall here, but then it gives you information about time, and it doesn't actually give you doesn't actually give us direct rainfall amounts. So, for example, here it says 0 centimeters, but then it doesn't give us any more rainfall amounts. Really what it gives you is time. So I think actually this axis, really we kind of need to change the problem a little bit. Let's change it to say it can be modeled as a piecewise linear function of time in days during heavy rainfall, okay? So I am going to change that. Sorry about that. Okay, so let's say of time during the rainy season. And that way this axis will not represent rainfall anymore. It will be time. Okay, so I know that that's kind of unfair to change the problem, but well, it didn't really totally make sense before, so now we can do it. But anyways, so at time 0, we had 0.4, and then after 9 days, we have 0.89. Okay, let me connect those dots. And it says that it's linear. So we have a line between these two dots. And then actually we just keep going for 2 weeks. It says rainfall peaks after 2 weeks. So I'm going to go all the way to 14. And now my picture is getting kind of messy, so maybe I'll redraw it. I think I will redraw this. I'm just going to make it a bit smaller so I can see what I want to see. Okay, so this was times 0, and then we've got, let's say that's 14 and 9, and we know we have a point here, and we have a point here, and we peak at 14, And then we start coming back down because it's decreasing at the constant rate of 0.07. Okay. So that's going to be my model, or my picture, rather. And what points do I know? I know this point right here. It's 0, 0.4. And I know this point, it's 9, 0.89. I don't actually know this point, but what I do know is the rate for the second piece is negative 0.07. That's from right there. Okay, so my model, let's call it m of x, or rather m of t, for mosquitoes at time t. It's going to have two pieces. The first piece is this piece, which is, where is it valid? It's valid for x between 0 and 14. And for that piece, I'm going to use mx plus b. And we'll actually do that in just a moment. The b value is 0, and the m value, well, actually, I can get it from this first point. It's if the run is 9, then the rise is 0.89, so that's 0.89 over 9 times t. So that's 0.89 over 9 times t. All right. And for the second piece, we can't use mx plus b. The second piece is this piece. I'll do that one in red. This is the second piece. I can't use mx plus b. I have to use mx minus x1 plus y1 because I don't know the y-intercept, okay? But what I do know is that this one's valid for x larger than 14. And I know its slope is negative 0.7. And it's going to be t minus, what's t1? So I need these coordinates at this point right here. So I'm running out of room. Let me write this again down here larger. So that's negative 0.7 t minus 14. And then the only thing I don't know is what is y1. So to get y1, I just want to know, since these two lines connect, if I can just figure out what this first line is at 14, then I'll know what the second line is at 14. So basically, I just need to put 14 into this. So that's going to be 0.89 over 9 times 14. And this will be my second piece. Now, I haven't simplified it, but that is the equation. Okay, so there's my model. And the maximum number of eggs per acre, do you see that that's just going to correspond to, actually it's just going to be the y-coordinate that we were just talking about. So it's going to be 0.89 over 9 times 14. So let's go ahead and figure that out. That's 1.384 approximately. Repeating, million eggs per acre. And part B, express the per acre number of mosquito eggs in millions is a piecewise linear function of rainfall in centimeters. Well, guess what? We just did that. Although we did change it to not be rainfall, we changed it to be as a linear function of time during the rainy season. But we did do that. That's what this model is right here. So we actually did the problem already, the major part of the problem. We did it in sort of an unusual order, but nevertheless, we did do it. Okay, so there is problem number 8, kind of, after we altered it a little bit. All right, I will do problem 9 in the next video.